Let's start with a wild thought. What if the entire story of life on Earth didn't actually begin on Earth? Today, we're diving into panspermia, the incredible and, pretty controversial theory that the seeds of life, maybe even our own ancient ancestors, came here from the stars.
I mean, really think about it. The theory of panspermia basically forces us to ask this one blunt question. Are we all aliens? Could it be that every single living thing on this planet, from the smallest bacteria to you and me, is actually descended from extraterrestrial life?
You know, this whole debate really boils down to two huge ideas. On one side, you've got abiogenesis. That's the classic theory we all learned in school. Life just sparked into existence from non-living chemicals right here in Earth's primordial soup. But on the other side, you have panspermia, this radical idea that life was an immigrant, that it arrived here, fully formed from somewhere else in the cosmos.
So let's get into it. What is panspermia actually proposing? And how could life possibly survive a journey across the endless, empty void of space?
The name itself is pretty perfect. It comes from the Greek for seeds everywhere, and that really captures the core concept. Now, here's a really crucial point. Panspermia doesn't actually try to explain how life first began. It just relocates the problem. It suggests that initial spark happened somewhere else, and Earth was just seeded with the results.
Okay, so the whole idea of microbes hitching a ride on an asteroid sounds a little like science fiction, right? But there's one part of this theory that is backed by some seriously compelling evidence. And this, right here, is the key distinction to make. The strongest case we have isn't for fully formed living organisms traveling through space. It's for the delivery of the essential ingredients of life, the complex organic molecules that are the fundamental building blocks. This version of the theory is sometimes called pseudopanspermia, and the evidence for it is, well, literally written in stone.
Take a look at this number, 92. That is the number of different amino acids, the building blocks of proteins, that scientists discovered inside a single meteorite that crashed down in Murchison, Australia, back in 1969.
Now here's where it gets really mind-blowing. Out of those 92 different types of amino acids, only 19 are common in life here on Earth. This was the smoking gun. It proved that complex organic chemistry was happening out there in the solar system, completely independent of our planet. And even crazier, the meteorite's amino acids showed a preference for a specific orientation, a left-handedness, which just so happens to be the exact same preference all life on Earth has. It's like the cosmos gave Earth's chemistry a massive head start.
And the Murchison meteorite wasn't just a lucky one-off. As you can see here, from comets like 67P to asteroids we've recently visited like Ryugu and Bennu, our space missions are finding again and again that the essential ingredients for life are all over our solar system.
All right, so delivering the ingredients for life seems totally possible. But what about the main event? Could an actual live-in microbe survive that incredible, brutal journey through space?
I mean, a microbe trying to make this trip would have to survive an almost unimaginable gauntlet. First, it would have to survive being violently blasted off its home planet by an asteroid impact. Then it would face the deep, drying vacuum of space, followed by maybe thousands, even millions of years of being bombarded by sterilizing cosmic radiation. And for the grand finale, it would have to survive a fiery plunge through a new atmosphere.
And this challenge isn't just theoretical. Look at this chart. Scientists took one of the toughest, most radiation-resistant bacteria on Earth, this amazing bug called Deinococcus radiodurans, and they exposed it to a space-like vacuum. The result? A 4 orders of magnitude drop in survival. That means for every 10,000 bacteria they started with, only 1 survived. And that's just from the vacuum, not even counting the radiation or the heat.
So the science really points to this conclusion. The idea of naked microbes just floating through space being pushed by starlight, what's called radiopanspermia, is pretty much biologically impossible. The only way a microbe could realistically survive is if it were shielded, buried deep inside a big chunk of rock. That version of the theory is called Lithopanspermia.
And this brings us to the more speculative and, let's be honest, the more sci-fi versions of the theory. What if life's journey through space wasn't an accident at all?
This table does a great job of summing things up. We've talked about lithopanspermia, the one that's really challenging but still plausible, and we've talked about radiopanspermia, which is not so plausible. But look at that third one, directed panspermia.
Directed panspermia is exactly what it sounds like. It's the wild hypothesis that an advanced alien civilization intentionally seeded Earth, and maybe other planets, with life. And I know it sounds like a movie plot, but this wasn't just some fringe idea.
It was seriously proposed by brilliant scientists, including Francis Crick, yes, the guy who co-discovered the structure of DNA.
And his argument was based on something pretty profound. The fact that every single living thing on this planet, from an amoeba to an elephant, uses the exact same genetic code. Well, to Crick, that seemed a little too neat. It hinted at a single, deliberate origin point, almost like a piece of software that was installed just once, right at the very beginning.
Of course, you know the saying, extraordinary claims require extraordinary evidence. And this timeline of the famous Martian meteorite ALH 8401 is the perfect cautionary tale. Back in 1996, the world absolutely exploded with news of what looked like fossilized microbes from Mars. But after decades of intense scientific debate and analysis, the final consensus is that those little shapes were just formed by normal geology, not life. It set an incredibly high bar for any future claims.
So, this all leads to the big question. How are we actually looking for answers today? How can we finally figure out if we have some cosmic relatives out there?
Finding life on Mars would be the ultimate test. Think about it this way. If we discover Martian microbes and their biochemistry is totally alien to ours, maybe they use right-handed amino acids or some molecule other than DNA, that would strongly suggest life started independently on both planets. But if they use the exact same DNA, RNA, and left-handed amino acids as we do, well, that would be overwhelming evidence for a common ancestor and pretty much prove that panspermia happened right here in our own solar system.
And the best part is, we are actively searching right now. Our rovers on Mars are digging for these very signs. We're planning missions to the incredible ocean moons of Jupiter and Saturn. And the James Webb Space Telescope is literally sniffing the atmospheres of distant planets, looking for chemical hints of biology, like a gas called dimethyl sulfide, which on Earth is produced almost exclusively by life.
So, to bring it all home, it's clear that panspermia isn't just one simple idea. It's really a spectrum. As this chart shows, the idea of life's ingredients being delivered from space, pseudopanspermia, is strongly supported by the evidence we have. Transporting actual life inside rocks, lithopanspermia, is plausible, but faces huge, huge challenges. And directed panspermia? Well, that remains fascinating, but highly speculative.
Which leaves us with this final, absolutely thrilling thought. If one of our rovers finally strikes gold and finds life buried beneath the red Martian soil, what will that discovery truly mean? Will we be making first contact with a genuinely alien life form? Or will we simply be shaking hands with a distant, long-lost relative?